Hello everyone. In this video, I'm going to provide an overview for discrete and continuous random variables, probability mass functions, and cumulative distribution functions. So a quick overview of the video. We'll begin by defining random variables. We'll talk about some examples of discrete and continuous random variables, and we'll go through the definitions of probability mass functions and the cumulative distribution functions. So we define a random variable, which I will denote by RV, as a function x from a sample space S to the set of real numbers such that for any outcome omega in our sample space, there is an assigned real number x of omega. We usually drop the functional notation and we just use a lowercase x to represent values of this function capital X. So remember, capital X represents the function itself. The lowercase x's would represent values that the function can take on. So there are two main classes of distributions of random variables. There's the discrete random variables and the continuous ones. So the discrete random variable can be defined by saying that the range of x is either finite or countably infinite, and we use a probability mass function to help us calculate probabilities. Okay, with this type of function, we actually get probabilities as the output of the function. Then we have continuous random variables. And with a continuous RV, the range is uncountably infinite. Okay? In this case, we use calculus to deal with these continuous random variables. And in addition to having a special function, a PDF, we have to use some calculus to get our probabilities. And so the idea is we will actually calculate probabilities by taking integrals of our PDF. PDF, as we'll learn later, stands for probability density function. So some examples of discrete random variables would be the number of cars sold at a dealership during a given month, number of houses on a certain block, number of fish caught on a fishing trip, number of complaints received at the office of an airline on a given day, number of customers who visit a bank during any given hour, and the number of heads obtained in 3 tosses of a coin. So note with some of these, it's easy to see that the number of values, number of possible values is finite. And then with others, they may not be a clear upper bound. So we might say something like the number of possible values is countably infinite. You could still count them, but you just don't have an upper bound. For example, the number of fish caught on a fishing trip. Okay, it could be 5, 10, 20, 30. There's no upper bound. So technically, this could be infinite, but it's still countable, okay, which makes this the number a discrete value. Some examples of continuous random variables would be the height of a person, the time taken to complete an examination, the amount of milk in a gallon. Okay, now we do not expect a gallon to contain exactly 1 gallon of milk, but it's going to be either slightly more or less that we could measure, okay, and the weight of a fish. So for all of these, there's a certain interval that might be reasonable, but within that interval, there's an uncountable number of possibilities. So in addition to being infinite, it's also uncountable. Now, we define a probability mass function, sometimes abbreviated as a PMF, of a discrete random variable to be given by, say, P of X, and by this we mean the probability our random variable X is equal to a specific value X. So, as an easy example, let's let X be the number of boys in a 3-child family. Okay, so now our X is an example of a discrete random variable. You can assume the values 0, 1, 2, or 3. And we could say the probability of 0 boys in a 3-child family is 1/8, 1 boy 3/8, 2 boys 3/8, and 3 boys 1/8. And these could be obtained by listing the set of possibilities in terms of B's and G's. If you think of all the 3-letter sequences with B's and G's, there's 8 possible, and 1, for example, where there are no B's, would be the GGG sequence. That's how we might get 1/8. Now, the cumulative distribution function, abbreviated CDF, is defined really for all random variables X and is given by, we use the notation capital F, and usually the subscript for our random variables X. So the CDF of value X is the probability that our random variable X is less than or equal to a specific value of X. So given a PMF, it's easy to find the CDF just by adding successive values. We'll do that in the next example. But you may also see in some of the exercises that given a CDF, one can work backwards to actually find the PMF. So here's an example. Suppose we have a discrete random variable that has the following PMF. So X can take on these 5 values, 1, 2, 3, 4, 5. These are the probabilities. We want to find the CDF function, capital F of X. Okay. So F of 1 is just equal to really the probability X is 1, and this would be 0.4. Sorry, there's a little typo here. It should be 0.4, not 0.04. F of 2 is the sum of the first 2 probabilities, so 0.4 plus 0.25, so this would be 0.65. F of 3, the sum of the first 3 probabilities, and you can see this adds to 0.85. F of 4, the sum of these 4 probabilities, 0.95, and finally, F of 5 is equal to 1. And notice if you were to graph something like this, you would get something that looks like a step function. And you'll see plenty of these as you go through the textbook. Finally, let's take a look at another example, and we'll put together both the probability mass function and the CDF. So dice are always interesting for probability questions, and it's usually fun to think about some unusual types of dice. For example, there are 5-sided die, 7-sided die, and so on. You can see all these different ones. And these are used in various games. So let's think about a 5-sided die, okay? And imagine that the 5 sides that are possible to come up are 1, 2, 3, 4, 5. They're all equally likely. So a probability mass function would be given by, we could break it down. Probably X is 1 is a fifth, X is 2 is a fifth, in case you get 1/5 for all these values. Or in general, we might just say that P of X is equal to 1/5. The CDF, so here we have F of 1 is the probability X less than or equal to 1 would be a fifth. The probability, not the probability, but let's say F of 2 is the probability X is less than or equal to 2. So now we add up the first two values. We get 2/5. F of 3 similarly is 3/5, and we get 4/5, and then 1. So these sections 7 and 8 in the textbook lay the foundation for a lot of things to come. They're fairly short. We've gone over some of the basics. I would advise you to go through the notes and the exercises. The exercises are fairly fast. Okay, I hope you've enjoyed the video. That's it.